Good morning, everyone. Today we're going to continue our look at the radius of convergence by seeing how all of these rules, or I guess there's only two of them, we're going to see how those rules apply to power series. So let's go ahead and get started. Okay, we have something here which admittedly is probably a little bit forced here with John Glenn and the Friendship 7 capsule. We should probably show you the Friendship 7 capsule, or at least a mock-up of it. This was the capsule in which John Glenn became the first American to orbit the Earth. And, well, I don't think we're going to say a whole lot about that. And we're going to take a look at this quick review, and we have for which values of x does this series 3 plus 3x minus 1 plus 3x minus 1 squared, for what values of x will that series converge to the geometric sum 3 over 1 minus the quantity x minus 1? And with a very quick review that if this is a geometric series, and it is a geometric series, it's going to converge to its geometric sum only if the absolute value of the ratio is equal to or is less than 1. So this work proceeds pretty easily. We start by saying that the absolute value of a ratio must be less than 1. Actually, we start off by signaling to the reader that we know the series is geometric. That's a really good first step, so don't forget it. And then we just go ahead and substitute what we know is the ratio of this geometric series, and that happens to be x minus 1. And then we compare it to x minus the center is less than the radius, and see if we can make a one-to-one correspondence. I see here that we don't have to do any additional solving. So then we say that this series the center is 1 and the radius is 1. Then for any series, we say that the series converges for x epsilon center minus radius to center plus radius. And then when you work out all that math, you get that the series 3x minus 1 to the n converges for x in between 0 and 2. Remember, we got 0 and 2 from 1 minus 1 and then 1 plus 1. And this geometric series workflow is really nice. It's really simple, it's compact, there's a straight path to follow, and there are no deviations. So this geometric series business is really nice for us. And this leads us into some new vocabulary, which tragically is at the bottom of the page, not usually where you want to start something new. And this is the first time we're seeing the idea of absolute convergence. And if the absolute value of a series converges, then the correct vocab to use is that the series itself converges absolutely. And absolutely here is a reference to the absolute value. It's not a reference to, yeah, totally, absolutely, bro. That's not what it is. It's just absolute value. And this is nice because that if the series does converge absolutely, then the series is just said to converge. You don't need the absolute value. The series will converge even without the absolute values. Now, if the series doesn't converge absolutely, but it still converges, we say that that series converges conditionally. And conditionally means here on the condition that it's not an absolute value. So, converges absolutely, converges conditionally. They're both showing convergence. And then if we mash those two things together, we get what's called just the plain old interval of convergence. So it's any place where the series converges either conditionally or absolutely. Okay. So the interval of convergence is made up of all the places where the series converges absolutely and all the places where the series converges conditionally. That tends to be really confusing for a lot of people, but this won't stop you from getting a 5 if you are not completely, great with these definitions, but I hope you will be. It's nice when you guys are able to talk or speak like mathematicians, unlike me, who can barely speak at all. So, you know, use the vocabulary of a mathematician. That's why we're here. So the next couple of sections that we're going to be doing, this one, of course, we are already in the middle of it. And then section 10.5, these are going to all be about finding convergence of a power series. And so this brings us to this idea of there are three things that could happen when we speak about convergence of a power series. The first thing is that power series could converge for all real numbers. And that's what happens with the series for e to the x, cosine x, and sine x. The series converges no matter what the value of x is. You may need a lot of terms of the series in order to get a meaningful approximation, but it is possible. You don't need to recenter at all. You just need to have a whole lot of terms. Now, on the other side of it, the series may only converge for a small set of numbers. An interval of convergence is what we would call it. And usually that interval of convergence will have a center and will have a radius. So it'll create a nice, it's an interval. What am I saying? A nice interval of convergence. Now the endpoints of the interval, you know, the lower end and the right end, those two numbers may or may not converge, but everything inside that interval will definitely converge. Failing that, the power series would be said to be only convergent at the center of the series. Now at the center of a power series, all of the terms are going to be equal to 0, except maybe the first term. So you basically get a series that's just equal to the first term. So of course that's going to converge. It's just going to converge to that one number. Our major concern is going to be the second way that things converge, where they converge on a interval only. So kind of as a reminder, you can write your interval of convergence in a couple of different ways. The first way is going to be using the absolute value, where the x minus the center is less than the radius. And the next way is with interval notation, where we say x, the Greek letter epsilon, and then a left endpoint and then a right endpoint. That's called interval notation. The series is going to converge for every number that is strictly inside that interval, and either the endpoints are either going to include or exclude. Depending on whether you use brackets or endpoints, you can say whether or not the interval includes an endpoint or excludes the endpoints. Bracket is include, parentheses are exclude. Like we were mentioning yesterday, convergence of power series, just like convergence of non-power series, that's really going to be two big strategies. And so convergence strategy number 1, we've already met that, and we're going to show another example of that. And that happens when you get a series that is geometric. This is the easiest and best case scenario because, like we saw earlier, the rules are very straightforward, the interval is very straightforward, and there is very little solving to do, if any. So let's take a look at this example. We've got the series 2 to the n and x plus 1 to the n. The first thing I ask you to do is to write out those first 4 terms, just to see if this is actually a geometric series. Okay, so for here, to get from one term to the next, it seems as though we need to multiply by 2, and we also multiply by x plus 1. Since we're only using multiplication, we say that the series is geometric, with r equal to x plus 1. And the next step here is to solve absolute value of r is less than 1. And I just noticed that my ratio is actually incorrect. It is 2 quantity x plus 1. So the absolute value of r is less than 1, which means the absolute value of 2 times x plus 1 is less than 1. Multiply both sides by 1/2, and you get the absolute value of x plus 1 is less than 1/2. Compare that to the sentence x minus center is less than the radius, and we can see the center is going to be -1, and the radius is going to be 1/2. Easy, right? Next, for the interval of convergence, we start with x epsilon, center minus radius to center plus radius, and then we solve that. Center minus radius is -1 minus 1/2. That's -3/2. And then -1 plus 1/2 is -1/2, giving me my interval of convergence -3/2 to -1/2. And we're done. Pretty easy problem, I think. I mean, if you've made it all the way to this point in calculus, and this is really difficult, then, well, I don't want to be too harsh about that, but this is not that difficult. Strategy 2 is actually the place where we get in a lot of trouble. So in strategy 2, we only use it if the power series is not geometric. And if that happens, we go to the ratio test to determine the interval of convergence. So just to refresh your memory, here is our review of the ratio test. If we take the limit of the absolute value, the limit of an plus 1 over an, if the limit is less than 1, the series converges. If the limit is greater than 1, then the series diverges. And if the series is exactly equal to 1, then the ratio test is inconclusive. So here's some adjustments we're going to make for power series, because yesterday or last lesson we only used the ratio test for series that were not power series. So because of power series, the terms can be negative. So to use the ratio test, what we're going to do first is we're not going to test the series. We're going to test the absolute value of the series. If we do that, then we're going to create the absolute, or the interval of absolute convergence. Again, absolute means absolute value, nothing else. When you do that, you're going to get the endpoints of that interval of absolute convergence. And no, I'm sorry, back it up. We're going to do this, and we're going to force our interval to be less than 1, because our interval is going to contain the variable x. So we want to know for what values of x will the ratio be less than 1. That's going to create an interval, or an interval for x. Now, when x is equal to the end of the endpoints of the interval, then algebraically, that limit that we created for the ratio test is going to be equal to 1. So the endpoints of that limit may or may not converge conditionally. So we're going to have to test those, and that's what we're going to do in section 10.5. So let's look at this example problem. We've got a really typical looking power series. You've got n x minus 1 to the n over 5 to the n. And the first thing that we always want to do, because we don't want to waste our time with a ratio test if we don't need to, is we want to check to make sure this is not a geometric. And to do that, we just write out the first 4 terms and see if it's a multiplication thing. So let's take a look at this series after we've written them out. The first term is 1x minus 1 to the first power over 5 to the first power. Actually, let's do this. Let's take a look at the numerators and denominators separately. So starting off with the denominator, to get from one denominator to the next, we just need to multiply by 5 on the denominator. So we're multiplying by 1/5 to get from each term to the next term. That's good because that's geometric. It only involves multiplication. In the numerator, the same thing happens with x minus 1 because we start with x minus 1 to the first power, to the second power, to the third power. So we're multiplying each successive term by x minus 1. But where this falls apart is that additional factor 1, 2, 3, and 4. That is not a multiplication thing. That is, that's a series thing. So because I can't get from one term to the next using multiplication, this is not a geometric series. And I would write down not geometric. So our next thing here is to do the ratio test, and nicely this problem has actually set up the ratio test for us. With this extra bit right at the end, we're making the limit less than 1 because we want to force this to show us when, for what values of x, this limit will be less than 1. So we're going to do some simplification. So the first thing I'm going to look for is any piece that's algebraic, and that's at n plus 1 over n. Let's put that in our limit. Next, I've got 5 to the n over 5 to the n plus 1. I actually know how that simplifies because, I did all my homework yesterday, and I know that the 5 to the n is going to cancel out with a 5 to the n on the denominator, and the only thing that's going to be left is a 5 in the denominator. And then the next thing that we have, that's going to be the x minus 1 to the n plus 1 over x minus 1 to the n. Now these are going to simplify pretty much exactly like the 5 to the n and the 5 to the n plus 1. The x minus 1 to the n plus 1 has an extra factor in it, so that's going to stay in the numerator, and the x minus 1 to the n power on the denominator is going to cancel out completely. So let's see what we have here. We've got n plus 1 over n. That needs to be in the limit because it has obviously n's. The 1/5, well, the 1/5 doesn't have any n's with it, so actually it doesn't need to be part of the limit. So I'm going to put it in the front of the limit. And that brings us to x minus 1 over 1. Now that also does not have any more n's in it. So I can take it out of the limit, but if I do that, I have to keep the absolute value because we have, x as a variable. So that may or may not be positive. And that gives me the limit of, well, we have the absolute value of x minus 1 over 5 multiplied by the limit of n plus 1 over n. And then again, we force that to be less than 1. Well, the limit of n plus 1 over n, that's going to be equal to 1. And we have so many things to do in this problem that if we're going to take the time to, do everything we need to do to show that that limit's going to be equal to 1, we're going to be, kind of losing some valuable time. So hopefully you can look at that limit and you can see that it's equal to 1. So this gives me the absolute value of x minus 1 over 5 is less than 1. And we're going to multiply both sides by 5. And that gives me that the absolute value of x minus 1 is less than 5. So this says that when the absolute value of x minus 1 is less than 5, then the ratio test is less than 1. Let's not lose sight of that this came from a ratio test. So all we need to do is say that the absolute value of x minus 1 is less than 5, and then my series is going to converge absolutely. Let's compare that to x minus center is less than the radius, and we can see that the center here has to be 1. We can also see that the radius has to be 5. So bringing it all down, what is the interval of absolute convergence? Well, for any interval of convergence, it's going to be the center minus the radius to the center plus radius. How much is 1 minus 5? Yeah, that's negative 4. And how much is 1 plus 5? Of course, that's equal to 6. So the interval of absolute convergence is the interval from negative 4 to 6. Now, as a reminder to you, I'm going to remind you that the series may be conditionally convergent at x equals negative 4 and x equals 6. We just need to develop more tests in order for us to actually look there. Because if I try the ratio test when x equals negative 4, it's going to be inconclusive. Same thing with 6. This brings us to our important ideas, and the first one is convergence for power series. And we have two strategies here. Same two strategies from yesterday. The first one is for a geometric series, and if you discover that your power series is a geometric series, then all you need to solve is radius less than 1, and you're going to get the interval of convergence. There's no such thing, or you don't have to worry about interval of absolute convergence or conditionally convergence. None of that matters for a geometric series. The next is for a non-geometric series, and in a non-geometric series we use the ratio test. And this is going to come into, there are 3 things you need to do here. The first part, and the part that we did today, is to find the interval of absolute convergence by using the ratio test on the absolute value of the general term. Then you're going to test the endpoints to determine if the endpoints converge conditionally, and that's what we're going to do in section 10.5. Once you have interval of absolute convergence and conditional convergence of the endpoints, you're going to combine those 2 things together to create just the interval of convergence. And that's also going to be in section 10.5. So let's find the interval of absolute convergence for this series. We've got x minus 4 to the n and over 3 to the n. And let's see what kind of series we have here. Okay, writing out the first 4 terms, that definitely looks geometric to me. So this is a geometric series with the first term equal to 1, and the ratio is x minus 4 over 3. So the absolute value of the ratio has to be less than 1, which means the absolute value of x minus 4 over 3 needs to be less than 1. And with a little multiplication, we see that x minus 4, the absolute value, has to be less than 3. Compare that to x minus center is less than the radius, and we see that the center is 4 and the radius is 3. Finally, every series converges for x between the center minus radius and the x plus the radius. Maybe I should say every type 2 series has an interval of convergence of center minus radius to center plus radius. And that simplifies to the interval x between 1 and 7. No problem. Pretty easy. So let's move on to number 2. Number 2 has the interval of absolute convergence, and we have root n x minus 1 to the n over 2 to the n. Oh, also we have a negative 1 to the n power. Now I'm going to kind of shortcut things here for you and say that this is not a geometric series. And the thing that tells me this is not a geometric series is I've got an n here, that square root of n is not a part of the exponent. So as soon as you see an n that's not part of an exponent, you kind of know that this isn't going to be geometric. Not geometric, so we have to use the ratio test. Okay, well, this is quite the setup for the ratio test. I've gone ahead and I've put things together. Over in this first part of things, we just changed all of our n's to n plus 1. And in our second factor, we just have the reciprocal. Now, putting everything together, I notice that I've got negative 1 to the n plus 1 over negative 1 to the n power. And those are also inside an absolute value. So actually, they don't matter. I'm going to pretend they don't exist, because if you take the absolute value of negative 1, you're just going to get a 1. So I'm not even going to worry about them. The next thing I see are these absolute values. And for those absolute values, if I have an absolute value on top of an absolute value, I'm going to make a habit of putting them both under the same absolute value. So what do I mean? The absolute value of n plus 1 over the absolute value of n. I mean, the square root of n plus 1 over the square root of n is just equal to the square root of n plus 1 over n. That's going to be a little bit easier to compute. Now the next part here I see is the x minus 1. So I've got x minus 1 to the n plus 1 on the numerator and x minus 1 to the n on the denominator. I know that those are going to cancel out, the x to the n power, and that's going to leave me with, well, just an x minus 1, which has no n. So I'm going to put that on the outside of my limit. Okay, what's the next part I see? And I think I'm moving to the denominator now, and I have 2 to the n plus 1. Now 2 to the n over 2 to the n plus 1, that's going to just simplify to 1/2, which again has no n, so I'm just going to put it on the outside of the limit. And we're going to force this entire thing to be less than 1. So this looks pretty good, looks pretty promising here. Inside that limit, I'm going to divide everything by n. So we need that entire beautiful disaster to be less than 1. If I let n approach infinity now, 1 over n is just going to go to 0. So that gives me the limit of 1, which is just 1. So now I have something which will give me some results. Because when the absolute value of x minus 1 is less than 2, then the limit of an plus 1 over an is going to be less than 1. This is going to give me my interval of absolute convergence. We'll compare that to x minus center is less than the radius, and that tells me pretty plainly that the center is 1 and the radius is 2. Just like the previous problem, we're going to do 1 minus the radius to 1 plus the radius, and that gives us -1 to 3. And the interval of absolute convergence is -1 to 3. So once again, these are the major tools that we're going to be doing to find our intervals of convergence in AP Calculus. Hopefully I've made things easy for you, but you're still going to need a lot of practice. Putting all of these things together doesn't come overnight. So have a good one. I'll see you all next time.